Hi, I'm back with another video, and this time I'm going to be discussing the instant redstone logic. And because of a recent discovery by cubehamster, there are now two ways to do this. If I remember correctly, Tavi Ryder is the person who originally discovered this. These are some gates that a friend of mine built for his instant piston computer. And it runs on a 5 clock. He's got an 8-bit computer. And the way the dual rail logic works, these are dual rail, which means there are 2 wires for each bit. So for an 8-bit computer, there's 16 wires. And they're always on. And then if this one flashes off, that means it's a 0. If this one flashes off, that means it's a 1. Because they run on inverted power. So you can see the wires are always on. And then if they flash off, that means that one has updated. So that's why you see for this here, which is an OR gate, there are 5 inputs for the OR gate. One is the clock, which is this here, and then there's an A, a not A, a B, and a not B, and then you can see there's an output and the inverse of the output. And so that was the way it was traditionally done. And then cubehamster discovered this cool little trick with glowstone like this, which is where it's one of the interesting properties of glowstone, because it's been moved so many times between a solid and a transparent block. You can put wire on it, but it won't propagate a signal downwards. It will not send a block update downwards. And so you can create these, and if you watch the torches on the side, you can see these both update at the exact same time. And that's the property that I've been working with. And so I've created quite a few logic gates here. This is an AND gate. This assembly here, the actual gate itself starts here. This is just to provide both of the inputs at the same time. So if either one of them is on, you get nothing. That's your output, by the way. If they're both on, we get an output. If only the other one's on, nothing. This here's an OR gate. It activates when one or both of them is on. This one here is your output. So if I flick either one of them on, it's going to update. Or if they're both on, it's going to update. And as some of you may know, every component in a computer, every logic gate, every device can be built from NAND gates or NOR gates. In real life, NAND gates are used because they use one less transistor than every other gate, and so they're faster. So to have a NAND or a NOR, you need an AND gate or an OR gate. In this case, I have both. And you need a NOT gate. It turns out that with single rail logic, which is what I'm using here, but there's only one wire, NOT gates are the hard part. Because with dual rail logic, all you have to do is flip the wires. Just put the right one on the left and the left one on the right, and you've effectively inverted the signal, as far as the system cares. For single rail logic, the way it works is there's a clock signal, and if this pulses, if the output pulses at the same time as the clock, that is interpreted as a 1. If the output does not pulse when the clock pulses, if it remains constant, that's interpreted as a 0. And so I finally did create a NOT gate here after going through quite a few iterations. And if I turn this clock on, see the output's a 0, or the input's a 0, and the output's going to pulse every clock cycle. So that works fine. Now if I change this to a 1, the output is not going to pulse. So that's the NOT gate. And this is another NOT gate here, without all the fancy stuff removed. And it's just got the clock inputs and everything labeled. This is an AND gate. The important part about the AND gate is that the output, which is this block here, is that it's equidistant from both of them. Because if it's not, if this one's one block farther away than this one, or one block closer, it won't work. So they have to be the same distance away. So you can't make this much smaller, if any. And so this here is an XOR gate. This doesn't have a clock line. All of the clock inputs are just labeled. Then you've got an input here, an A input, and a B input. And then this is just another NOT gate and AND gate floating. This is all culminated in this, which is a full adder. The pink is the clock line again, and this is a particular design of adder which uses 7 AND gates, which you can see here. Some of them have 3 inputs down here, and 3 NOT gates, which are underneath of here. And then all this in the back and on the side here, this is all just busing to move the wires down. Then there's an AND gate here for controlling the output. And I had to move this onto a buddy's server to even test it, because the way redstone works in multiplayer is that it will slow down the redstone ticks instead of slowing down the server. But if I do that in single player, my FPS drops from 100 something down to 10, 5. So I can't even reliably test this in single player. I have to test this in multiplayer. And I made an architecture for a computer, but I never went through with the design. I may someday, I just haven't yet, where I will build a 1-bit version of the machine and then just copy paste it upwards, and then just tie all the inputs and outputs into their proper locations. So it is possible to create a computer with this. So I just wanted to show this off and say that, yeah, it's been done. And if you want designs for these, if you want to make your own computer, I can provide schematic files. I can do tutorials for the XOR gate or for the other little gates. I'm not going to do one for this one because this took hours to build. So I can provide a schematic file if necessary. Otherwise, I'm not going to do a tutorial for this, just because it's so massive. And yeah, that's all. So thanks for watching. Like, comment, subscribe, whatever. And see you next time.